The final topic in this section considering structure functions is structural importance. Structural importance will be defined here, and the particular type of importance that we're looking at was devised by Birnbaum, so sometimes you will see this out in the literature or if you do a web search as Birnbaum importance. Here's the notion: certain components are more important than others in determining whether or not the system functions due to their position in the system. I'll underline the word position because later we're going to hit something called reliability importance, and reliability importance takes into account the reliabilities of the components, whereas structural importance only takes into account where they are positioned in the system. So here's a question: what component do you consider the most important component in the system below? Well, in that particular system, you'll notice that if component 1 fails, the system automatically is going to fail. Whereas, for example, if component 2 fails, the system will still be operating with component 3 as a backup. So in some sense, when you look at that system, you would say the most important component in the system is 1, and then 2 and 3 are tied for second with a lower importance. So what we want to do is we want to develop a mathematical measure of importance. And here is a mathematical statement. Phi of 1i and x minus phi of 0i and x is equal to 1. The only way to have that happen is to have a 1 for the first term and a 0 for the second term, which will give you a 1, which is to say, when there is a 1 in the ith position and when there is a 0 in the ith position, the system goes from operating to failed. Now let's go back to the original system and consider I equals 1. Take a look at that first component. If you institute this equation here and look at the left-hand side of it, you know when I equals 1, you are going to have a 1 in the first position in all cases for the first term in this expression. Now in the second term, what we do is we take that 1 and we take it from functioning to failed and ask, did the system go from a 1 to a 0? Well, it turns out for 3 of the 4 state vectors that you see below, namely these right here, correspond to the system going from functioning to failed. This vector here corresponds to a functioning system. So does this vector. So does this vector. However, if you take this 1 and you replace it with a 0, the system comes down and this equation is satisfied. Now in this particular case, what we do is we're starting with a system that is not operating. So that's going to give you a 0 minus a 0 here, which is not equal to 1. Okay, let's formalize that in a definition. The structural importance of component I in a coherent system of n components is this expression right here, and it is denoted by I sub phi of I. Here's the term that we were looking at on the previous slide. This is kind of an unusual summation here. The reason it's unusual is rather than going across an index, for example, most summations go from I equals 1 to n, this is a summation across vectors. And what this says is it's a sum over all of the vectors x such that the ith component takes on a value of 1. And where does that I come from? That I comes from the index right here. Finally, this normalizing constant right here is going to keep all structural importances between 0 and 1. And the reason why is there are 2 to the n minus 1 terms in the summation. So if you divide by 2 to the n minus 1, it will keep the structural importance between 0 and 1. Here are a couple notes. The summation runs across all of the sets of the 2 to the n minus 1 state vectors such that xi equals 1. Second, the summation counts the number of these vectors for which component I being operating minus component I being failed results in the system going from the operating state to the failed state, and that's what this equal 1 is right there. Number 3, the summation gives more weight to those vectors for which the failing of component I results in system failure. Fourth, for any coherent system, this structural importance will lie between 0 and 1. And that's 1 inclusive, but it will not be 0 for I equals 1 to n. And the reason why is we have assumed that we have a coherent system, so each component is relevant. And finally, I sub phi of I is useful to a design engineer. It will help point to the components that are critical in the system design in terms of their importance to the functioning of the system. All right, here's an example. Let's say we want to compute the structural importance of all 3 of the components in this system. We know because there are 3 components, there are 2 to the 3rd power, which is 8 possible system state vectors. The summation from the structural importance will run across 4 of those 8 state vectors. So let's start with component 1. We want to calculate his structural importance. To calculate I phi of 1, we want to run the summation over the 4 system state vectors which have a 1 in the first position. So of those 4 vectors, 3, namely the last 3 that are listed, correspond to phi of 1ix minus phi of 0ix being equal to 1. So I phi of 1 will be 1 over 2 to the n minus 1. That'll be 1 over 2 squared, which is 4. This first vector goes from failed to failed, so it's a 0 minus 0. The second vector goes from functioning to failed. Third vector, functioning to failed. Last vector, functioning to failed. So you get 3 divided by 4. Now, if you run through that same scenario, of course, you'll be summing across different vectors and calculate I phi of 2 and I phi of 3. In both cases, you will get 1/4 because in the case of components 2 and components 3, only one of the 4 vectors takes you from functioning to failed. So you get a lower number, a lower structural importance for the second and the third components. Once again, keep in mind structural importance says how important is this component to the functioning of the system based on their position in the